Okay, so we're going to start again with this background material, and I'm going to move through chapter 3 through 5. Okay, so here we go. Chapter 3. It's going to be a quick one. Operational amplifiers and where they're used in chemical instrumentation. Basically, they're used everywhere. If you consider the signals that are coming from different kinds of sources, right? I mean, the signals that you look at in UV vis, the signals that you look at in IR, all those different signals, you're going to get very small signals out, and you need to be able to convert those. And so, operational amplifiers are really important. Again, the circuitry, hopefully, you'll get an idea from your previous physics that this is what these look like, and this is how they're being amplified. You're going to get different input and different output out, right? And so you may have to invert this stuff. You have to use these high input impedance difference amplifiers. So the difference between the positive and the negative channel, and then you have to use a voltage amplifier and then another low impedance output amplifier, and you get the output. All right. So let's think about this for a minute with something like a UV vis, okay? And this is what we've got in this picture. You've got the light source. That light source travels through a sample. That sample hits a phototube. A phototube is a light-sensitive cathode. That light-sensitive cathode gives off electrons. The electrons hit the anode, collect at the anode. They go through, and they're amplified, and you get a readout. Okay, so that would be where they would be used. Conductance cells, very important, right? I mean, if you're looking at conductivity, then you're going to have very small signals coming out. And again, these amplifiers are really important. Down here on the bottom of this in B, you've got a double beam system. Okay, so you've got a sample on the left, the reference on the right, and the source comes out and it's chopped in half, and it goes half to the sample, half to the source, or half to the sample, half to the reference, sorry, and then it hits a photoconductor and again has to be amplified. All right, on to chapter 4. So with the advent of computers, everything now has to be digitized, okay? So the typical detector response would be an electrical signal, right? An electrical signal is not digitized, and so we have to use these digital converters, or analog to digital converters. And so the signal at the bottom would be the more digital looking signal, okay? Again, the response, the digital signal, and then how you would then convert that. This is just one of those one of the schematics of how we interact with chemical instrumentation. So a human operator in part A would have the computer and the mass storage, and they would be controlling that and the analytical instrument. In the second one, you have more of a computer, human operator, analytical instrument, but the computer and the analytical instrument are talking to one another. And then in the bottom case, which is most of what we have in our laboratory, where you have the operator through the computer controlling the analytical instrument. Okay. So what goes in, right? So you get a signal that goes in. The cell in digital is either a 0 or 1. The data input is a 0 or a 1. The data output is a 0 or a 1. And then according to what happens in the cell, you get the output or the read that is a 0 or a 1. This is a long slide that basically walks you through all the possibilities of what needs to happen as you bring something into the lab, as you test it, as you validate it as you generate reports, as you store those reports, and then as those reports are sent out. Now, how does that happen? Well, this is not something that we have in our lab, but it's something that you might encounter in a job, okay, out in the real world, where they have these laboratory information systems or LIMS, where they're handling the data. And there's a database, there's all sorts of different input from the different labs, the different instruments within a lab. It all brings it into kind of a centralized, again, database that allows different people to access it, depending on who they are and whether they're allowed to, and all those kinds of things. All right. Chapter 5, Signals and Noise. Now, in a lot of cases, the problem that we have is that we've got a very strong source, okay, and we're looking at a very small signal that may get through, or a strong source that excites a sample, or a lot of different things that go on. One of the problems is that you don't get the background noise to get it to cancel out. And so what this thing is showing is something that would be called a chopper. And in the chopper, the motor spins whatever, in A, it's got little slits in it, and B, it's a solid device. And as these things spin, you know the timing of them, and they will either cut out the beam, and you've got dark noise, and so you can subtract the background, or they let the beam go through, okay? And so you're looking at the beam versus the background noise of nothing hitting the detector except any ambient that might be there, all right? So again, a blow up of that, you could imagine that thing spinning around, right? And more than half the time the signal's getting through, and then it's getting cut off. So this is it in a sample instrument, and in this one, this is basically the AA. You've got the flame in the middle there. You've got a source, which is a UV vis beam. It gets sent through. You've got a chopper again, where part of the time the signal is getting through, part of the time it isn't. It gets into your amplifier, and the amplifier can, obviously it can amplify both signals, and then you subtract out the one that is the background. Another thing in there is the wavelength selector. We'll get into a lot of that as we move forward. So what does that do for you? Well, if you've got signals like this, right? That top one, it's hard to separate the signal from the noise, right? And so if you increase the scans and you subtract out the background, continuously increasing the scans, you get 50 scans, you start to see the signal. You get 200 scans, you really see that signal. If you look at the 200 versus the 1 at the top, you couldn't imagine that signal was in there unless you, again, did these scans. If you're scanning, though, we're talking about a lot of time, okay? And so one of the things that we can do is, instead of scanning through the entire spectrum, which is what you do with some wavelength selectors, you could pulse a signal, okay, and take all of the wavelengths all at one time. And what you would generate is something like part A there, okay? That would be the information all at one time. So this is the signal versus time. You can Fourier transform that. When you Fourier transform that, you get a signal that is called the free induction decay. So now this shows the decay of the signal, and then in C you actually continue to manipulate that then you do an inverse Fourier transform, and you get back to an actual signal that now has subtracted out the noise in the background. Sometimes when you're looking at your data, you may need to change the way you look at it. Okay, and so here's this 5-point smoothing of integers at the top. Okay, so that's that's a signal, right? That's a peak. But you may want to look at it in a different way, and you may want to look at it with change over time. Okay, that's what a first derivative would be. So you may want to do that and actually find out where the biggest change is occurring. Right? So sometimes you're going to derivatize these. You know, A, B, C, and D here, different ways in which the signal was manipulated and smoothed. Not in a way where you lose any kind of analytical information, but using the techniques that we talked about before. You know, again, back to the idea that you've got computerized instrumentation. You guys don't have electronic notebooks, but certainly that is something that you may encounter out in industry. All right, thanks, and see you later.